questions about anything, then we can talk about it. But you guys are rolling, it looks like, right? What's on the exam? I have to go look. I kind of forget. So what are you guys doing?
We listed off a couple different questions so far. So
Okay.
in relation to like the ellipsoids and elliptical paraboloid and all of that, which ones we should know?
Which ones you should know. Okay, so so in your book, every surface that's of this form, something times x squared plus something times, y squared plus something times z squared plus A, B, C, D, E, F, G. Okay. In your book, everything of that form is accounted for.
Okay.
So these are called quadric surfaces because they're quadratic in all the variables. So for us, what's important is something of this form. A positive number times x squared plus a positive number times y squared plus a positive number times z squared is equal to another positive number. What's that one? So if A, B, and C are all the same number, then it's a sphere.
Ellipsoid.
So this would be an ellipsoid. So the cross sections are all ellipses in all directions. So all the cross sections are ellipses. So this is called an ellipsoid. And I wrote down, this is an ellipsoid which is centered at the origin. Now more generally, we could shift in all the directions. And then if we multiplied everything out, that would give us some linear terms also. And so, but basically, you can identify the type of surface just by looking at the leading coefficients of all the variables. So if the leading coefficients are all positive when you write x, y, and z on the same side, then you're looking at an ellipsoid. And of course, if they're all the same number, then you're looking at a sphere. Okay, so for example, if I wrote down here 2x squared plus 3y squared plus 2x, maybe I won't write 2, we'll write 4x minus 6y equals 3 minus z squared. Can you recognize what type of surface this is without thinking too much? I'll give you a clue. I've only told you about one type of surface. It's an ellipsoid.
Just not centered at the origin.
It's not centered at the origin, yeah. So you notice the coefficient of x squared and y squared are both positive. Now the coefficient of z squared is negative, but it's on the other side of the equation. So if we move it to the left-hand side, this becomes 2x squared, and why don't I collect all the x's? Plus 4x plus 3y squared minus 6y plus z squared, because I move it to the left-hand side, equals 3. And I left some blank spaces there. Why did I leave blank spaces? So I can complete the square and see actually where this thing is centered. Right? So if I complete the square in x, so it depends on what your favorite method is for completing the square. Usually I will factor out the leading coefficient. Is that what you guys teach this stuff, right? Is that what you teach?
Yeah.
Okay. So I'm going to factor out the leading coefficient of 2. And then what's left is not 4x anymore, but 4/2 x, which is 2. And I'll factor out the leading coefficient in y of 3, and what will be left is 6/3, which is also 2. And so what should I add in the x group to complete the square? Should take half of the middle coefficient, which will be half of 2, which is 1, and square it, that's 1. And in the y group, I should add also 1. And I can't just add 1 because I feel like it. I need to make up for it on the right-hand side. And even though I added 1 inside the parentheses, I was actually adding 2. So I'll add 2 to the right, and when I added 1 in the y grouping, I was actually adding 3. So I'll add 3. Okay, so this is 2 times x plus 1 squared plus 3 times y minus 1 squared plus z squared equals 8. So this is an ellipsoid centered at I guess x is -1, y is 1, and z is 0. Okay, so from that example, I hope you can see. If you're just worried about classifying the type of surface, only thing that matters is the leading coefficients. Okay? So the rest you can get by completing the square. Cool. So ellipsoid, you know. What else should you know? Something that looks like z equals some number times x squared plus some number times y squared, basically. So that's an example in which the leading coefficient in one of the variables is actually 0, or the quadratic coefficient is actually 0, and so the leading term is linear. Okay, so we have a linear term equals something times x squared plus something times y squared, and if both of those somethings are positive, then, let's see, well then the slices here parallel to the xy plane are circles if a and b are the same number, but otherwise they're ellipses. So slices parallel to the other two planes, xz and yz planes, are, so if I fix a value of y, this becomes z equals ax squared plus something. And so that's the equation for a parabola. So if I'm drawing pictures, the graph looks something like this. Okay, so some of the slices are ellipses, some of them are parabolas. What's it called? Elliptic paraboloid. Yeah, you can do all the combinations of those two words that you can think of. Elliptic paraboloid. So this is what the picture looks like if A and B are both positive. very similar. If A and B are both negative, then it looks exactly the same, but flipped upside down maybe. Okay, so this one you can recognize if the equation is quadratic in two of the variables but linear in the third one, and the sign of the leading coefficient is the same in the two quadratic variables. So for example, let's see, 2x minus 3y squared plus y minus 2z squared equals 4. So notice this is linear in x, it's quadratic in y and z, and the sign of the coefficient in front of the quadratic variables is the same. So this is more complicated than what was written here, but it's also an elliptic paraboloid. Now it's different in that the linear variable is x instead of z, which means it's going to open not up or down, but along the x-axis. I'm going to try to draw the graph of this one. No?
Do we have to draw on the exam?
Yeah, I mean, it's a good idea. So what would we have to do? So I'd want to write it in a form like this. And so I'm going to solve for x. If I solve for x, it gives x equal, means I have to divide everything by 2. 1/2 times 4 plus 3y squared plus y, or sorry, minus y, and then I'll leave a little space because I'm going to complete the square, plus 2z squared. So that looks like x equals 1/2 times 4 is 2 plus 3/2 times y squared minus y over 3, leave a space, plus z squared. So if I'm completing the square, what should I add? Half of a third is a sixth, squared, 1 out of 36. So I added 136 inside this bracket, and it gets multiplied by 3/2. So 136 times 3/2 is 1 out of 24. 1/24 is what I added, so I'll subtract then 1/24 to make up for it. So it becomes x equals 3/2 times y minus a sixth squared plus z squared plus 2 minus the 24th is 47 divided by 24. So if I were going to draw the graph here, this is going to open along the x-axis in the positive direction or the negative direction? Positive, because the coefficients in front of y and z are positive. And it's going to have the vertex at the point y is 1/6, and z is 0. Y is 1/6, z is 0, and what about x? What's the x coordinate of the vertex? Oh yeah, so you can check. If you plug in y equals 1/6 and z equals 0, you get x has to be 47/24. Okay, so y is 1/6, z is 0, x is 47/24, somewhere around there. Okay, so we have elliptic paraboloids, we have ellipsoids and spheres, and there was one more. So cylinder, yeah, cylinder is a good one. A cylinder shows up when one of the variables isn't there. So I kind of put that in a class by itself. I think there were two more, I think, that we said that we would remember.
Hyperbolic.
Yeah, the one that has hyperbolas as cross sections. So something like z equal some number times x squared minus some number times y squared. Or these are both positive numbers. Okay. So this type of equation, this is kind of the simple form. You can identify it because it's linear in one of the variables, and in the two quadratic variables, the coefficients have different signs. Then you're looking at something which, let's see, cross sections, the slices parallel to the xy plane are, so if I fix a value of z, I get constant equals something times x squared minus something times y squared. That's a hyperbola. So the slices parallel to the xy plane are hyperbolas. And the slices parallel to the yz and xz planes are parabolas, but they open in opposite directions. So the slices parallel to the xz plane are parabolas opening up, parallel to the yz plane are parabolas opening down. This one has the hardest graph to draw. Slices parallel to the xz plane are parabolas opening up, and slices parallel to the yz plane are parabolas opening down. So this is the one that looks like a saddle. Looks like a saddle. And what do we call it? Hyperbolic paraboloid. think those are the three things I asked you to please remember. Okay, so also on your list, you'll see things like hyperboloid of one sheet and hyperboloid of two sheets. So it's interesting stuff. But these are the three main quadratic surfaces I ask you to remember. And then also cylinders in general. If one of the variables is missing, then the graph is called a cylinder. And it looks like the graph of the equation in two variables, in two dimensions, shifted to all values of the missing variable.
We were looking at this one.
Uh-huh.
I'm having trouble with some of them.
Okay. Should we, maybe we can pull it up on the screen so everybody can see it big.
Okay.
Okay. All right. So the question was about matching matching formula for a function with its level curve picture with its graph, I think. Okay, actually, why don't I just download this? So, this problem, right? Number 3?
Yes.
All right, very good. So, there are 6 functions of 2 variables written here, and 6 level curve pictures. And we're supposed to match them. Okay, so how do you do it? Well, I can't tell you, some general way to do this. Let's just think about what are the kind of salient features of each of these functions. So for example, function A, square root of x squared plus y squared. Well, right away I noticed that it depends only on x squared plus y squared, which is the distance from the origin. And so that tells me the level curves must be circles, all of them. Okay? So, so whatever the level curve picture for this function looks like, all the level curves are circles. Does that help me narrow down the list? A little bit. So it's not 2.
Not 6.
And it's not 6. Okay. So maybe we should start with the ones that don't have level curves, which are circles, since we've already narrowed that down. So which ones do have level curves, which are circles? Certainly A, certainly B, certainly C. All have level curves, which are circles. What about D? Yes, level curves are circles. What about E? No. And what about F? Okay, so E and F are the only ones that do not have circles for level curves. How can I, so that tells me E and F must be 2 and 6. How can I tell which one's which? Let's see, E, this is a function sine squared of x times sine squared of y. It's periodic in x and it's periodic in y. That means the level curves should repeat themselves as we move in the x direction and as we move in the y direction, individually. Is it true for number 2? Say I start at this point. Does it look like there's a period such that if I move to the right by that much, the level curve picture will repeat itself? No, it doesn't. This doesn't seem to be periodic in the x direction, and it doesn't seem to be periodic in the y direction.
Sorry, what do you mean by it's going to repeat itself?
I mean, so my function is called f of x and y equals, and it's given by this formula, sine squared of x times sine squared of y. So it has the property that f of x plus any number times pi, or any integer, sorry, times pi, comma y, is the same as f of x y. And so, okay, so pick a point here. And let's draw some level curves around that point. Okay, so maybe the level curve going through this point corresponds to the value, I'm not sure, maybe 1/2. And then close by there's another level curve corresponding to the value 1/4, and another one corresponding to the value 3/4. Okay? Now, because the thing is periodic with period pi, if I move to the right by pi units, so just shift by pi, then the value of the function should be the same. So I should see also a level curve corresponding to the value 1/2 there. And not only should the level curve going through that point have the value correspond to the value 1/2, it should look exactly like the level curve over here shifted by pi. Because if I move a little bit on the level curve down and shift that by pi, it must also be on the level curve corresponding to 1/2. And so the level curves, when I say they repeat themselves, I mean literally pick up this level curve and move it pi units to the right. There should be another level curve corresponding to the same value. Okay. And likewise for the others. 3/2, 3/4, and 1/4. Okay. And that should be true for this function. It's periodic in x and periodic in y. So it should be true as we move in the x direction and also in the y direction. Okay. Okay, so that's a really nice property that we should be able to see visually in the picture. I don't see it in number 2. If I pick up one of these level curves and shift it in some direction, it's not going to sit right on top of one of the other level curves. But it is true for number 6. So look at the level curves in number 6. The level curve picture around this point looks exactly the same as the level curve picture around this point. This looks like a function which is periodic in both x and y. So there's only one option. It must be E. Any questions about that?
So then on the contour, can we just go to the contour and try to figure out which one's which for the graph?
So can we also find the graph corresponding to E?
That'd be D.
It looks like it would be D, yeah. So the graph is periodic in both the x direction and the y direction. That's right. Okay, and that kind of leaves us with F matching with level curves 2. How can we see it's true? So let's think about that. So even though this one also involves a trigonometric function, cosine, It's not, in general, periodic in the x direction or the y direction. You can check. Cosine of xy divided by 3. Okay, usually cosine has the period 2 pi. Since we divide by 3, maybe it has the period 6 pi. So this will be the same as cosine of x plus 6 pi times y divided by 3, which is the same as cos of, I guess we can write xy over 3 plus 2 pi y. Is it the same as cos of xy over 3? That was my original f. It is if y is an integer. But if y is not an integer, then in general, this could be anything. Right? Because I think y could be anything. Okay? Okay, so this thing is only periodic in x for certain values of y, when y is an integer. Otherwise, it's not. Okay, so how does this thing behave? Well, if either x or y is 0, then the value of the function is 1. So there should be a level curve corresponding to the value 1, which contains both the x-axis and the y-axis. Can we see it? I don't see it. It must not be drawn on there. Not all the level curves are always drawn on there. Right?
Bless you.
But what should the level curves look like? You can solve an equation. If cosine of xy over 3 is equal to some number, that means that xy over 3 should be equal to a different number, the inverse cosine of the original constant. And so the level curves look like this function, x times y, the graph of this, sorry, not this function, the graph of this equation, x times y equals 3 arc cosine of c. Which, if you want, is y equals 3 arc cos of some number divided by x. More or less like y equals 1 over x. Do you know what the graph of y equals 1 over x looks like? It looks like these curves.